Welcome everybody. This is a lesson for Algebra 2 on Module 1, Topic 2, Lesson 3, which is on exploring cubic functions. And so we are on page 133 of your book. We're going to identify what is a cubic function, and we're also going to look at relative maximum, relative minimum, and those terms. We're going to look at cubic functions using words, tables, equations, and graphs. We're going to interpret the key features of cubic functions. We're going to analyze cubic functions in terms of their mathematical context and in the context of a problem, a real-world problem. Okay, we're going to connect the characteristics and behaviors of cubic function to its factors. We're going to compare cubic functions with linear and quadratic functions, and we're going to build cubic functions from linear and quadratic functions. Okay, so let's start with a little review of the distributive property to multiply these different linear or quadratic things together. I'll do one, and then I'm going to let you do the rest on your own, okay? If I have a times 2a minus 1 times 5 plus a, I have three things. These are three linear factors. I could choose any two to start to multiply. I could choose the first two or the last two. It's up to you. I'm going to go ahead and distribute an a to this first one, which gives me 2a squared minus a. Okay, and then I'm going to FOIL or use distribution to just distribute the 2a squared, and then I'll distribute the negative a. So 2a squared times 5 is 10a squared. 2a squared times a is a cubed, or 2a cubed, to forget the 2. And then negative a times 5, do negative 5a, and negative a times positive a is negative a squared. So then we should check for like terms, and we do have some like terms here. We've got an a squared and another a squared term. So we're going to do 10 minus 1. So putting our terms in order by the highest degree, we've got a 2a cubed, and then I'll put the 9a squared minus the 5a. Okay, I'll leave you to do the other three. Go ahead and pause the video and give these other three a try. And then when you're ready, you can unpause the video to see if you got them right. All right, go ahead and check your answers. I'll box them up for you so you can see them. Pause if you need to kind of look at the work a little bit more carefully. This is number 4. I just ran out of room. Okay, so we're going to do a very famous problem in algebra, and that is the maximizing box problem, essentially. So here's our setup. The Plant-A-Seed planter company produces planter boxes. To make the boxes, it cuts a square from each corner of a rectangular copper sheet that is 12 inches by 18 inches. So this square right here. There's one taken out of each corner. Then it bends the sides to form a rectangular prism without a top. Cutting different sized squares from the corners results in a differently sized planter box. Plant-A-Seed takes sales orders from customers who request a sized planter box. Okay, so it's going to be helpful to really visualize what they're talking about before we get into this. So I have taken just a regular 8.5 by 11 piece of paper, and I measured a square out of I think I did 1.5 inches out of each corner, and then I cut those squares out. And you can see I labeled that dimension with h. That's your unknown here. We don't know what the size of the square is. Okay. The size of the square is going to change the size of the box. So if you fold along those sort of dotted edges, see if I can do this a little bit better by not doing it in the air. Okay, you can see it's going to fold up to be a box. Now this is the size of the box I get with 1.5 inches as there, or whatever it is, whatever h is. So you can see this dimension of this box basically becomes the height of our box, and then there's also a length and a width. Okay, another way that we can think about it is I'm going to show you something else. Okay, here is something on GeoGebra, which is an app that kind of can be very interactive. I'll put the link in your lesson so that you can play around with this. So you can see this is the length and the width of the actual piece of, I guess it's supposed to be copper sheet or whatever the original rectangle is. And you can see it folds up like I did into a box. Okay. The height is the h is the dimensions of the square in the corner. So as it gets smaller, you're cutting out little tiny little squares out of each corner. We can see that it's going to be a very shallow box. Okay, well, we can get pretty big. All right, let's make it bigger and bigger. But you can see it's going to restrict the amount of material that we have. So eventually you may not have a very big box. It's going to get skinnier and skinnier and skinnier. And it may even get to the point where you're just folding a paper in half and it doesn't make any sense. We'll talk about those special cases. Okay, so back to this. In our situation, the copper sheet was 18 inches by 12 inches. So we have to fill out this table for the width, the height, the width, the length, and the volume. So one thing we need to remember is the volume of a box is length times width times height. So we're going to be multiplying these dimensions together. So let's think about what happens when you take out a corner square side length 0. Essentially, you're not going to cut anything. In my example of using a piece of paper, if you took out a square that was 0 by 0, you get a piece of paper. You're not cutting anything out. There's nothing to fold. If there's nothing to fold, there's no volume to it. So your height, which is the same as the corner side length, is 0. Okay? So basically you just have this rectangle that's 18 times 12. So the width, we'll say, is 18 or 12, but basically your volume is going to be nothing. So actually I'm going to switch that around. Technically it doesn't matter which one you call the width and which one you call the length, but I'm just going to be consistent with the book. And so we're going to go this way for the width, or the length, and this way for the width. Okay, what if the square was 1 inch? Well, now you're going to cut out little 1-inch squares. Okay, so if it was 1 inch, this portion right here is going to be your new width or length. I keep mixing them up, I'm sorry. We're calling that the length. Oh my gosh, Okay, width is going to be this way, length this way. Okay. We're going to have to take that 18, but we're going to cut off the 1 inches on each side. So we're going to have to do 18 minus the 2 1 inches, which is going to give us 16. Okay, so we're going to put 16 here. The height is 1. The width is going this way. It's still 1 inch and 1 inch, so we're going to take 1 and 1 and we're going to cut it off from the 12, and that gives us 10. All right, now we have a volume that we can actually compute. Okay, we are going to do 1 times 10 times 16, which is 160. All right, let's do one more row, and then I'm going to have you do the rest of the rows yourself. Okay. So let's make it 2 inches. So all these little squares are 2 by 2, so they're a little bigger. So that's going to change this dimension. It's going to be from here to here. It's going to be, we have to cut off the 2 from the 18. So it's like 18 minus 4, so it'll be 14. And then along here, the 12, we're going to cut off the 2 and the 2, so it'll be 12 minus 2 times 2, 12 minus 4, which is 8. And then the height is just the same as this is going to be the square corner side length. These 2 rows are pretty much going to be exactly the same the whole way down. Okay. All right, now let's do our volume. We're going to do 2 times 8 times 14. Remember, you're just multiplying these 3 dimensions together. And that gives us 224. So we can see that that volume is increasing. All right, I want you to pause it. Okay, and I want you to do row 3, 4, 5, and 6. And you could do 7, but leave the last one, okay? So let's do 3, 4, 5, 6, and 7. You are going to notice a couple of weird things going on in a couple of these cases, and I want you to think about why that might be. All right, pause the video, give it a try. Okay, I'm only showing you rows 3, 4, and 5 right now. We'll talk about 6 and 7 in a sec. But go ahead and check your answers for 3, 4, and 5. So for 3, we had height of 3, width of 6, length of 12, volume of 216. For 4, we had height of 4, width of 4, and length of 10. For side length of 5, we had height of 5, width of 2, and length of 8, and volume of 80. So hopefully you guys noticed kind of like the volume was increasing and then it started to decrease. So if we go back to that thing that I was showing you, first, like, the volume's not very big in this example. These numbers are different. Let's just leave it there. 6, we'll do 6 and 8. Just nice whole numbers. Close enough. So you can see when the height was, or the H is tiny little squares, you get a very shallow box. The volume's not going to be very big. And then it's going to get bigger. The volume's changing. Then it starts to go down because your box is not very big anymore. Okay, let's think about these ones. So something weird starts to happen in rows 6 and 7. Okay. So in row 6, the height is 6. And then the width, well, the width is 12 without cutting anything. So if you start to cut off, if you make a square that's 6 by 6, that's going to go halfway through. This is 6 by 6. Okay, not the most, let me redraw that. Something like this. So 6 by 6, you're not going to have any leftover stuff left over. It's basically the square is so big, the two squares would take up the whole width, 12 inches. 6 plus 6 is 12. So there's nothing left for the width, which means you're going to have 0. The length will still have some leftover because you'll have 2 6s subtracted from 18. So you still have another 6 left over. My sketch is not to scale. But the volume would be nothing because 6 times 0 times 6 is 0. Let me see if I can get an example of that on here. Okay, look at this thing right here. It's just a folded line. It's completely flat. It has no volume because it's basically would look like this. Here's your box. Completely flat. It doesn't make sense, right? But that's why the volume is 0. Okay, if we look at row 7, you're even in more trouble because you're taking 7 and 7 away from 12. 7 plus 7 is 14. You subtract it from the 12 that you have, you're in the negative. Like, huh? This doesn't make any sense, right? Remember, you only have 12 inches here. So if you have 7 and 7 on both sides, let me see if I could just draw a new picture. This is 12, and I'm going to cut out a square that's 7 by 7, and then another one that's 7 by 7. That's impossible. I'm taking out more than's already there. I'm in the negative. So we could even say that it's like -2. And then there's still some length left, but you're going to get a negative volume. Doesn't make any sense. So this one is like, huh? And this one's like, huh? So there are some limitations here. You can't just use any score size because you're limited to the size of the sheet. Okay, let's think about H now. This is an important row. We kind of saw that the height and the square length side are the same. So this is just H. Here, what we were doing is we were taking 12 and subtracting each corner. Well, there was 2 H's. So we were doing 12 minus 2 times H. So looking back at this thing, if this whole thing is going this way, there we go. If this whole thing is 12, and this is H, and this is H, what we were finding was this part after it got folded up. So we were taking off 2 H's. And we were doing the same thing for the long way. It was just 18 minus 2H. And so your volume is multiplying those 3 expressions together. The volume is H times 12 minus 2H times 18 minus 2H, both of them in parentheses. So then now let's analyze the relationship between the height, length, and width of each planter box. What are the dimensions of the largest sized square corner that the company can cut out of its planter box? So they want to know what's the largest square that we can cut out. Well, we kind of saw that. The biggest we can go was 6 by 6, but then it didn't really like leave us anything, right? Because it would be completely cutting out this dimension here. 6, 6, 6, 6. And so you wouldn't really have much left to fold, but that's the largest we can take out. Basically, we can go with that, but it's not going to give us anything. So we could say something by like a 6 inch by 6 inch square is the largest. I mean, it wouldn't give us anything useful, but okay, write a function v of h to represent the volume of the box in terms of the corner side length h. We already did that. We're just writing it as a function now. It's h times 12 minus 2h times 18 minus 2h. We're just giving it a output of v of h now. Okay, so that was our getting started. We're going to keep going with this problem, though, in activity 1. Okay, so we're still going on with this. But we now have a definition of what is a cubic function. Okay, a cubic function is a function that you can write in the general form f of x equals a times x cubed plus bx squared plus cx plus d. So in quadratics, you had ax squared plus bx plus c. Basically, think of it as like we're putting an x cubed in front of that and shifting the letters. We make it so that a now is the coefficient of x cubed, b is the coefficient of x squared, c is the coefficient of x, and then we introduce d as our constant. Now this, if we FOILed it out and multiplied it out, distributed and did all that, would eventually look like a cubic function. Okay, so now what we're going to do is we're going to look at what does this thing look like when you graph it. And so these three people all looked at it using graphing technology to analyze the volume of the function and to sketch a graph. They disagree about the shape of the graph. Evaluate each student's sketch and rationale to determine who is correct. For any students who are not correct, explain why the rationale is not correct. Okay, so let's look at Louis. The graph increases and then decreases. It is a parabola. What do you think? If you look at it, it doesn't quite look like a parabola, and hopefully you see that the shape of the parabola is a little funky. So I do not think Lewis is correct. Let's look at Ahmed. The graph lacks a line of symmetry, so it cannot be a parabola. He's right. Parabolas must have a line of symmetry. If we were to try to draw this line somewhere, it just doesn't look like the same shape on either side. So I am going to agree with him. Okay, Heidi says, I noticed the graph curves back up, so it cannot be a parabola. She's absolutely correct because parabolas don't do that. Okay, now notice she must have zoomed out. Remember, when you're graphing something in Desmos, it's really important that you're looking at the whole picture. Something could look like a line if you're zoomed in real close when it's not. So let's use graphing technology to represent the cubic function v of h with the settings -10 to 15 and -40 to 400. So just to remind you what this is interval notation. This is basically saying x should be between -10 and 15, and y should be between -400 and 400. Or instead of y, we could say v of x or f of x or whatever. Keep in mind here, in our function, we were using h H is still your independent variable. So we kind of go back and forth between calling it X or H, and I should have said V of H here for Y, okay? So let's open up a Desmos window and see what we can see. So if you just go to Desmos and you type it in directly, this is what you see. It just looks like 3 vertical lines. But remember, you really got to look at the viewing. Let's zoom out. Whoa, this goes up and down and back again. But it's very condensed. So that's why we want to change our viewing window. So we're going to go to the little graph settings wrench. And under x-axis, I'm going to follow their directions and go from -10 to 15. So I'm going to type -10 to 15. Oh, it already looks so much better, right? We can even label this axis as H, okay, or length of square edge. Y-axis, we're going to go -400 to 400. And this is our volume, or V of H. Okay. We can see, we can kind of follow it around if we want to. It's going to go up and up and up. It's going to go down. It's going to wiggle around. Okay. Now let's answer some questions about it. So the 3 questions they want us to answer are: describe the key characteristics of the graph. What is the maximum volume of a planter box? State the dimensions of this planter box and identify the volume of the function. And is this volume the same or different in terms of the problem situation? I mean, is the domain the same or different in terms of the problem situation? Then we're going to identify the range. And what do the x-intercepts represent to this situation? Do these values make sense in terms of this situation, the problem situation? Okay, so for the key characteristics, I want you to look at the x-intercepts. Maybe some y-intercepts. Or intercept. Can't have plural if it's a function, right? And any other key things that you see. Okay, so I want you to pause. I want you to look at the graph, and I want you to identify what those are. Okay, so I do want you to go on to Desmos and type this function in. Practice typing in the function yourself so that you can identify these things. Okay, so go ahead and go on to Desmos, type it in, find those key things, and see if you can answer as many of those questions as possible. Okay, so let's identify the x and y intercepts and any other important characteristics that we see. So I have a little screenshot of our graph. Our x-intercepts are at 0, 0, 6, 0, and 9, 0. Okay. Our y-intercept is at 0, 0. It's just the same point right there. And some other really important points, you'll hopefully notice when you're in Desmos, there's some gray dots that you can click on. The gray dots indicate that it is an important point to the graph. This point right here is the highest part of this little hill. So we can see that it is increasing to that point. The volume is increasing. Then it starts to decrease on the way down. And then at this point, it starts to increase again. It's also important to note where our your volumes positive and negative, because you cannot have a negative volume. So in this section here or over here, these things don't make sense because the volume cannot be negative. It's just not possible. Okay, so for other, you could choose these other points. You could describe lots of different things. I'll leave that part blank. It just varies on what you saw. B, what is the maximum volume of the planter box? So the maximum volume is going to be the highest point on the graph. That makes sense. So if you're not careful, you can go like, oh, well, it's going to go up and up and up, isn't it? But remember that the largest H could be was 6, right? Because we would cut out that square, the two squares, and there wouldn't be anything left. Where's that picture, right? You cut out the 6s on each corner, you're not going to have anything left. The volume would have been just 0 because you don't have a width anymore, right? And you can see that in there. If you do 12, if this is 6, it was 12 minus 2 times 6, which is 0. Doesn't make any sense. Anything beyond that, you start to get negative, and it doesn't make any sense also. So when you look at this graph, we're really only going to focus in the portion where x is between 0 and 6, which is this part right here. And then you can see the largest volume. Well, this is h, and this is the volume at that h. So the maximum volume is 228.162 cubic inches. That's the largest volume you can get. And the dimensions for that, the height, which is the side of the square, was 2.35. I'm just going to round it to 2.35. The width would be 12 minus 2.35, which is about 7.3 inches. And then the width is 18 minus 2.35, which is about 13.3. So if you multiply these things together, you're going to get something close to that volume. I did approximate, so it's not exact. So identify the domain of the function. Now the domain of the function is just mathematically, we're talking about like what can you plug in for h? We can plug any number we want in. The domain of the function is all real numbers, which we can write as all real numbers. We can also say negative infinity to infinity. But the situation domain is very different. Basically, that h value could only go between 0 and 6. And it really should be bigger than 0 and less than 6. Somewhere between 0 and 6. For you to actually be able to cut out a square from each corner. Okay, so that's this pink portion that I was just looking. That's the realistic domain for the situation. So the range is going to go from a volume of 0 to a volume of about 228. So your realistic range is in here, and your realistic domain be the one between 0 and 6 in here. So I'm going to say from about 0 to, well, we're doing the situation domain. We could talk about the function in a second. So the situation, range, v of h was at least something, so greater than 0. but up to 228.162, that maximum volume. Now, the function's range is infinite. It's negative infinity to infinity. It's all real numbers. And we can see that because it's going to keep going down and down and down and down, even though that part doesn't make sense for the situation. And it's going to keep going up and up and up and up, even though it doesn't make sense for the situation. All right, and then our last question, what do the x-intercepts represent in this problem situation? Do these values make sense in terms of the problem situation? The x-intercepts are all when the volume are 0. These occur when the volume is 0. Do they make sense for the problem situation? Not really. Why would you make something that has a volume of 0, right? Why would you just fold the sheet in half and not make an actual planner, right? It doesn't make any sense. So no, these do not make sense. Okay, so I wanted to at least get through the planter problem with you. Let's look at a little bit of a definition here, and that is relative maximum and relative minimum. Okay, and this is pretty much the function that we just looked at. A relative maximum is basically like the top of the hill. A relative maximum is the greatest y value in a particular section of the graph. I think of it like the top of the hill. So this right here is your relative maximum. We don't say absolute maximum because it is not the highest point on the entire graph. And that is because of this arrow here saying we're going to keep going up. But it's the highest in that section, and that's an important point. A relative minimum is pretty much the same idea, but I like to call them the bottom of the valleys. Okay, so it's the point with the least y value in a particular section of the graph. So you got a little valley here, the bottom of that valley. So there is your relative minimum. It is not the lowest point on the entire graph. We can see that the graph over on the left is going to go down much further. Okay. A customer orders a particular planter box with a volume of 100 cubic inches, but does not specify the height of the planter box. Okay, so you can basically solve this graphically. So they're giving you the volume, but you don't know what h is. So you can set 100 equal to your function. But we're not going to solve it algebraically. We're going to look at your graph, and you're going to make a horizontal line at y equals 100, because y is the volume. It's going to go like this. It's going to cut through your function, in this example, 3 times. We want to identify where it's going to, what h's it's going to cut through. Now, this third one we can very much ignore, because it doesn't make any sense, because it's past the point where our domain is. Remember, from 0 to 6. Okay? So you could just use the first point of intersection where h is 0.4. So let me show you that on Desmos. So we have y equals 100, and it's going to graph the line. You can literally just click on the dots where it intersects. We're going to ignore this last one, and either one of these first 2 would technically work to give you that volume. They would make very different shapes, but they would both work.